Hi, my name is Michelle O'Halloran. I'm a final year student in the University of Limerick. This is my presentation for the module CE4028. I'm a part of Group 7 and the name of the module is Energy Efficient Buildings. So today I will go through how to set up a steady state model for thermal analysis of a building. This is when there is no heat flow through the building. We are evaluating the thermal equilibrium of a system. As I mentioned in our previous presentation, our group are focusing on the new Bon Secours Hospital in Limerick, as shown here. This hospital has two sections, and we will be focusing on the section at the far side. Here are some more photos shown here. So it's more of the rectangular section. The building has two floors, so the ground floor and the first floor. So this here is the ground floor plan. At the side in the legend you can see the areas are color coded based on their usage. So you have kitchen, restaurant, radiology, etc. So we zoned our building based off these. We assumed that certain sections would be heated at certain temperatures. And here again you can see the first floor plan, and again at the side on the legend they are color coded again based off their usage. So again we zoned the first floor based off what we assumed temperatures would be at certain times of the day. And from this we created our heating schedule. So our heating schedule is shown here, and you can see we have our different zones down the left hand side, and we have the temperatures we think they would be at. So our hospital needs to be heated 24/7 as it is constantly occupied. Some areas like linen storage are heated at certain times just to prevent dampness and mold. Now that we have an idea of the temperatures which zones need to be at, and we have an understanding of our building, we now need to build a thermal resistance network for our building. Here shown is a snapshot from AutoCAD showing the ground and first floor plans layered on top of each other, which will become useful later on when determining areas and which zones are in contact with each other. Each element in the building holds a certain thermal resistance value. We need to analyze and identify each of these before building our resistance network. Here is a table of the different components of our building which we identified as thermal resistors. So at the top we have external walls which consist of insulation, reinforced concrete, wall ties, cladding. Then we have windows, which consist of probably two panes of glass and an air gap in between. And then we have internal walls, which consist of plasterboard, insulation, a midspan noggin, and an air cavity. And then we have partitions, which consist of blockwork and plasterboard. Then we have our first floor slab, which consists of reinforced concrete, finishing, drop ceiling, and vinyl. Then we have our ground floor slab, which consists of reinforced concrete, sand binding, waterproof membrane, ground insulation, and hardcore. And then we have our roof slab. Now I will run through how to obtain a resistance value for a specific element. Heat can transfer in three ways: radiation, convection, and conduction. Conduction occurs between objects by direct contact. Convection is heat transfer by the movement of a fluid, such as water or air. Radiation is the transfer of heat through electromagnetic waves. An example of this is how you are heated by the sun. I have a solution written out here of how to obtain a resistance value for the ground floor slab. You can see here in black I have marked the thickness of each material. R1 is taking place above the surface, so this mode of which heat is transferred is through convection. This is represented as 1 over HA. H is a convective heat transfer coefficient which differs for each fluid. Then for R2 to R7, the mode of heat transfer is conduction. This is represented as delta X over Ka, where delta X is the thickness of the material, K is the conductance of the material, and A is the area. As this is a ground floor slab, heat needs to travel through the soil to get to the ambient air again. The heat travels through soil, much like water, using flow net patterns. The resistivity of the soil for R8 is 1 over Ks, with S being the conduction shape factor. We assume this value to be quite high and therefore are not considering it in our calculations. The R9 value is convection through the air. The area here is also quite large, so it is assumed is nearly equal to 0. So by adding all these resistance values together, we can get our RTH total. From that we can get our R value, and the area here is 1 meter squared. So then our R value is 0.19911 meters Celsius per watt. And then we can get our U value by putting 1 over our R value, and here we see it's 5.022 watts per meter Celsius. I have another example shown here for a double glazed window. I wanted to show this as it is a bit different to the ground floor slab, as this also includes radiation and modes of transfer which are occurring in parallel to each other. So you can see here we have a similar layout to the ground floor slab, but here we have a value for radiation resistance, which is T1 minus T2 all over the effective emissivity by the stress by the area multiplied by T1 to the power of 4 minus T2 to the power of 4. I think it is important to mention here that T1 and T2 need to be entered into the formula in Kelvin degrees. The temperatures here can be estimated at this time, so we said T1 was 20 degrees Celsius and T2 is 7 degrees Celsius, so when you change those over to Kelvin, they're higher. The emissivity is a value representing the effectiveness of a surface to emit energy as thermal radiation. This value is dependent on the material properties. Some windows have low emissivity coatings on them in order to save energy in buildings or reduce the heat loss. So when we summed all these resistances together, in the same way as the last slide I showed with the ground floor slab, although this is just a bit different with the resistors in parallel, Um, but when we sum all those together, we find that the R value is 0.05 degrees Celsius per watt, and there is a high U value of 4.266 watts per meter degree Celsius. So this means there is high heat loss through the windows. And then for our calculations further on, we combined the resistance for the windows with our external walls in parallel. So we said that the windows made up 35% of the outer face of our building. So now with all that information, we can make our resistance network. So there is a resistor for every zone which is in contact with each other, and then there is a resistor for every zone to the ambient temperature. And what I did to make it a bit clearer was I color coordinated the two floors. So on the ground floor, all my nodes are in pink, and then on the first floor, all my nodes are in yellow. So some of the yellow and the blue nodes, when they're connected, I just color those in green. Although everything is part of the same resistance network, I just did that to make it a bit clearer. So just to be clear that this is all one resistance network and that the green isn't separate to the blue. So then moving on, as I showed you earlier with the AutoCAD, that you can find the areas from AutoCAD. So you can see here I tabularized for the ground floor slab the area of each element in each zone. So this represents zones in contact with each other, and it just represents the area of each element in each zone. And then if the zones are in contact with each other, so for the ground floor slab, zone 1 is in contact with zone 1, so that's why I wrote the 833 here and so on. So you might have different zones in contact with each other for different elements. So then, as I described previously with the windows and the external walls, we did a similar thing for the ambient temperature. So here there is 3 elements working in parallel. So you have the external wall, the ground floor, and the roof. So we calculated a weighted average, and we found a resistance value for each zone for the ambient temperature. So then from all that information, I could tabularize each of the zones, areas, and R values, which we found previously. And then by dividing the R value by the area, we could get a resistance value for each of the resistors in our resistance network, which was previously shown. So for each zone, we have a resistance value for each of the resistors coming from the node. So then, just to show you our heating schedule again, now we have another zone added on. It's not a zone, but it's just the ambient temperature. So now we have all the temperatures for every hour of the day. In the previous slide, I just showed you the temperature which I found for the ambient temperature, and I just found this by applying a sine value and a diurnal variation of 2.5 degrees. So the average temperature in Ireland all year round is usually about 10 degrees Celsius. So as the temperature changes throughout the day, we found this sine wave, which we applied to our temperature. So, as this is a steady state model, we can apply our conservation of energy equation. So this says that the sum of each heat flow at each node must equal to 0. So when we rearrange this, we can get a value for Ti, and we can apply this to each of our nodes. So I just did out an example here for a few of the nodes. So you can see up on the left hand corner, this is an example for node 1, and then we have 5 resistors coming out from it. So to find our unknown temperature, we can use this equation and we can solve them simultaneously. So solving them simultaneously can be a quite long process, and there is quite a few unknowns, so we can use an application called Excel, and we can use iterative calculation function in Excel to give us our unknown values. So now that we have all our unknown temperatures in each zone, we can rearrange our equation to get our energy requirement. So I just did out an example for node 1, and just to make sure to put in your minus sign beforehand, as when you rearrange the equation you have a minus in front, and that gives you an answer for the energy requirement to meet the temperature you want in watt hours. So you can see here the energy which is required to get the zone to the temperature you wanted. You can see in the zones that we required 0 degrees for, that they're at 0, and you can get the total heating load for each hour over the course of the day, and we had a total heating load per day of 7,044 kilowatt hours. So we had about 15 heating scenarios, so I just did an example of 2. So this is an example of the heating scenario 1, so you can see the different zones of the building require different energy outputs for the scenario 1. And here is the example for scenario 6. So you can see that there is some heat transfer through the building, even though those zones aren't being heated. For example, zone 9, the energy output is 0, but it's still at not a high temperature, but it's at 9.6 degrees, which would be higher than what you'd expect. Thank you for watching. I hope you enjoyed my presentation. Bye for now.